So what does gabapentin do to the channels? The channel, they mean VGCCs, or voltage-gated calcium channels. You have neurotransmitters that will go across that area between the axon terminal and the dendrite in that area in between there is called the synaptic cleft. The other reason is due to sodium-potassium pumps. So these are going, to my knowledge, all the time, all right? It is a form of active transport. That means it requires ATP, all right? So what the sodium-potassium pumps will do is they will remove, or they will pump out 3 sodium ions and then allow in 2 potassium ions. The reason why you need active transport for that, you need ATP to do that, is because you're moving the sodium against its concentration gradient. You're also moving those ions from an area that's negative, which is inside the cell, to positive. Well, the sodium doesn't want to go that way. It wants to stay where it's negative. It doesn't want to go into the positive area, so you got to force it. The neurons got to force it. So it uses ATP and say, nope, you're moving whether you like it or not, and it pushes it up there, and then it allows the potassium into the cell. Think about it. You're removing 3 positive, and you're only allowing in 2 positive back, so you're down 1. Well, these sodium-potassium pumps are occurring all the time. So those two are 2 reasons that I'm aware of that it creates this discrepancy where you have it's negative inside, positive outside. Well, that's good for us because that discrepancy is what allows the action potential to take place. Well, if you're bringing this quote-unquote flood of sodium or flood of calcium into the neuron, which is negatively charged, what happens to the charge? It goes up. It's going from negative 70 to negative 55 to negative 40 to negative 30, and eventually it can come positive. Now that process from where it goes from negative 70 and it's continuously going up and eventually into the positive is called depolarization. And so as these ions come flooding in, they reach the axon hillock, which then will take it down the axon. All right, so remember we have the soma, the dendrites, the axon terminal here, and then we have the axon. That's like the long tube, so to speak, that then connects the two. And it can be very, very long, depending on where the neuron is. But there, the axons will go down there on its way to the axon terminal. And so I've talked about this before. In that axon, you will have gaps in the axon there because the axon is covered by the myelin sheath, which is like shielding to the neuron. It's shielding to it, just like I have a cable here, my iPhone cable, or actually this is for my Samsung phone. It needs shielding on a cable where they're shielding on the neurons, and that's the myelin sheath. Well, there are gaps in that myelin sheath where additional sodium floods can occur. There's voltage-gated sodium channels there that will allow additional sodium to come in. So if you have a strong enough action potential and then it goes down the axon and it reaches that first break in the myelin sheath, well, then that opens up the voltage-gated sodium channels and allows more sodium in to continue that action potential to get down to the axon terminal. Now, those breaks in the myelin sheath are called the nodes of Ranvier. I think it's actually pronounced nodes of Ranvier. I think that's how you pronounce it, but I kind of like saying it nodes of Ranvier because it sounds better, like I'm all mad. You know, it has those voltage-gated sodium channels to allow in more sodium to then basically amplify that action potential so it can continue on and then eventually reach the axon terminals. Well, the VGCCs are there in the axon terminals. They're monitoring the voltage of the neuron. They're saying, okay, what is it now? Well, it's still negative 70 millivolts. We're good. Well, then as those sodium ions come in, the membrane potential goes up, or you can say down depending on how you look at it. When I say up, it means just getting closer to 0 and then it's going to turn positive. And I think right around negative 20 millivolts, somewhere in there, is when those VGCCs start to open and they start allowing calcium in. And then that facilitates the binding of the storage vesicles with the neurotransmitters, it facilitates the binding of those to the presynaptic neuron cell membrane. And then those neurotransmitters can be released through a process called exocytosis. All right, it can be released into the synaptic cleft, and then they can bind to receptors on the dendrites of another neuron and continue what we just talked about earlier. All right, and so those VGCCs are right there in the, I believe it's called the active zone, where those storage vesicles that are next to be released full, storage vesicles full of neurotransmitters that are next to be released into the synaptic cleft. That's where those VGCCs exist. So now we've kind of explained, I don't know, not really briefly, but we explained what the VGCCs are for. Now we get to gabapentin. We get to the crux of the question, like, well, what does it do? It negatively affects it. Well, how does it negatively affect it? Right? Well, first of all, let's go over what gabapentin is. It is a medication. It was made originally to be a GABA analog, which means it was supposed to be similar to GABA, which is an inhibitory neurotransmitter, so it helps to kind of calm down neuron activity. And it does. It is similar in chemical makeup to GABA, but it doesn't bind to the GABA receptors. So if we go back to the picture of the calcium channel here, right? Gabapentin is a ligand, meaning it binds to the alpha-2 delta subunit. There is a domain in the alpha-2 subunit called the VWA. It'll be abbreviated as that. It's the von Willebrand factor A domain. Now, within that domain, there is something called the Midas motif. Midas is an acronym. It stands for metal ion dependent adhesion site. Now, gabapentin, it is a ligand for arginine amino acids that are right by that von Willebrand factor A domain of that alpha-2 subunit. So it'll bind there. And by binding there, it disrupts the functionality of that Midas motif.